Okay, hi. So welcome back to the tree playlist on data structures and algorithm. So that I have started with a new subtopic on trees, that is binary search trees. Okay. So first of all, let me check that my audio is there or not. Okay. Audio and video is there. Fine. So let's start with today's topic. Over here, we need to insert a node in the binary search tree. So in the last video, we have seen that how to search an element in binary search tree. So if you don't know anything about BST, basically, see, if I'm standing over here, the elements on the left hand side will be always going to be lesser than the 10, and the elements on the right hand side will be greater than 10. So over here you can see this 13, 11, 15, 12, which is greater than 10. So this applies to each and every node. If this is there, then we can say that this is a binary search tree. Okay, so I believe that you got the definition of binary search tree. Now let's see the problem statement. Now over here, let's see the problem statement. They will be giving us the root of the binary tree along with the value that we need to insert. Now we need to return the root of the modified BST. So obviously when we are going to insert a new node into the current BST, the tree will be modified, right? So we need to return the root. And over here there is a note that it is guaranteed that the new value that we are going to insert, that value is not present in the binary search tree. Okay, so whenever we are going to insert a value, that value will be a new value, by the way. Okay, and you can just read it on your own. This is not that much important, this line. Okay, now over here, if I'm going to insert 17 into this binary search tree, obviously, since we want to maintain the property of the binary tree, so when we are going to insert this 17, the property has to maintain. So if I'm standing over here and if I want to insert 17, obviously it has to be inserted on the right hand side. So I will be going over here. Similarly, I will be comparing this 13 with 17. 17 is greater than 13, so I will be going on the right hand side over here. Same applies over here as well. So I will be going on the right hand side. So over here there is a vacancy. No node is present on the right hand side of 15. So I will be going to insert this 17 over here and connect it like this. So I believe that you got the problem statement, okay, and how the modified binary search tree will look like after inserting any node. Okay. Now let's see that how we can solve this. See, visually we can see easily that we just need to compare where to go left or or we need to go on the right hand side, and based on that we can connect it. But how we can do this programmatically? So we will be doing it over here. Now if I'm standing over here, I will be going on the right hand side, again right hand side. Now when I will be going on the right hand side, I can see that the address that I will be passing, which is null. So if the root value or the parent, or that means the address, is null, at that time I just need to create a new node. On that node, sorry, in that node, the value will be 17. That's it. After creating a node, we need to return 215 that hey, this is the node that I have created. Please attach it on the right hand side. Why right hand side? Because we have came from right part. Okay, I believe that you got it. So when this node will be created, let's say 17, and the address is, let's say, AD 10. So we will be returning this reference to the right part of 15. Okay, and the same thing we will be going to apply for each and every node, because we don't know that whether 13 on the right hand, whether the right hand side of the 13 does any node is there or not. Okay, so basically we are going to return the address whether the node is present or not. We are going to address, we are going to return the address. Okay, so I'm so sorry that I'm confusing you, but we are going to return the address. Okay, now let's see over here. Let's try to have a pseudocode. This is a function in which they will be passing the root and the value. Now, first thing we will be going to compare is the root value is greater than value, the current value. Now see, over here I can see that the root value is greater than the current value. So basically I need to go on the left hand side. So I will be calling the same function, but I will be saying that, hey, take this value and connect it on the left hand side of that. Okay. So I will be passing the root dot left. That means the address of the left child and the value. Okay. So this is basically a recursion. But if the root value is lesser than the value, then I need to go on the right hand side. Okay. So basically I will be calling the same function, but I will be passing the right part, or we can say that the address of the right child and the current value. Okay. And whatever this function will return, we need to store that in the root dot right. Okay. Now if root is null, so over here we have seen that if the root is null, okay, so when I was comparing 15 with 70, 15 was lesser than 70, so I need to go on the right hand side. But when I was passing the address of the right children of 15, which is null, so it means that there is a vacant point, so I can create a node. Okay, so I will be creating a node. So tree node, data type of node, new node equals to new tree node and 70. Okay, so over here the node is created. Now we need to return new node, and that's it, we are done. Okay, so again, this was a very easy, even though the question state that is a medium level, but it was a very easy code. If you have came from the background of how to insert a node in the tree, in the basic tree, that means a binary tree, or how to search a node in the BST or a basic tree, you will get how how this is working. Okay, now talking about the code performance of this code. See, since this is a binary search tree, so either I will be going on the left hand side or right hand side, not both. So due to that reason, the time complexity to insert will be order of log n in the average case. Okay, what do you mean by average case? If the tree in the binary search tree is balanced, that means most of the time each node is having two children. Okay, so basically it will balance like this. Okay, so due to that reason it will be logging. But if it is a skew tree, that means it is growing in this manner only, and the new node that you are going to connect, that node is also connected over here only. So at that time the uh, time complexity will be order of n. Okay, in the worst case scenario. So due to that reason, what I'll do, simply I'll just have order of h over here. So basically order of h represents height. Okay, height of the tree. If it is balanced tree, then the height of the binary search tree will be log n. But if it is a skew tree, that means it is growing on in this direction or in this direction, then the height will be n. So due to that reason, I have written order of h. Same goes for space complexity as well. Order of h. Okay, basically in the tree series I have explained that the space complexity of the trees, so you can just refer to that playlist as well. Okay, so that's it. Again, if you didn't understand, you can dry run it by yourself. You will get the intuition that what is happening. Okay, so that's it, and I thank you so much for being in the live streaming.